Hey, cool cats and kittens, welcome back. Going into section 2.5, I'm pretty sure this is 2.5. Okay. So we're going to discuss how to draw graphs of functions if you know how to draw graphs of something kind of close. Okay, so remember in the previous section we did what the book referred to as a library of functions. So a couple basic things like x squared or root x that we know how to draw the graph of, and now we're going to learn how to transform those graphs into the graphs of other functions. Okay, so the main objectives, there are a few different things we're going to be covering. The first is vertical and horizontal, there it is, vertical and horizontal shifts. We're also going to do what they call compressions and stretches. I tend to call these vertical and horizontal shifts and compressions. Also, then at the end, there are ways to draw graphs based on reflection techniques. Okay, so first example, use the graph of root x to obtain the graph of root x plus 2. And what's important to note, by the way, this is not the square root of x plus 2. It's the square root of x plus 2. Okay? Find the domain and range of the function. So the function root x plus 2, what it really is, it's the same thing as root x, except what we've done to it is we've added this plus 2. So if f of x is root x, then what we have here is just root x plus 2. So anytime you get out a certain value for root x, what you get out here is the same thing but 2 larger. So if you were to plug in x equals 0, okay, instead of the square root of 0 being 0, you would get this function equals 2, because it's just 2 larger. So if we make this table, okay, root x, the square root of 1 is 1, the square root of 0 is 0, the square root of 4 is 2, and here are some decimal approximations of root 2 and root 3. And all we have to do to go to our function here is add 2. So 1 plus 2 is 3, 1.4 plus 2 is 2.4. So everything on the graph here is how we already know how to draw root x, and everything just goes up by 2 units. So this is what's called a vertical shift. Okay, we took the graph we already knew how to draw of root x, and we just moved the whole thing up by 2. Okay. So it's just the same graph, but up by 2 units. Okay. We were also asked to find what's the domain and range. So the domain is the same. Okay, our function is right here. The only obstruction is that we have this radical, this root x, and so that x just has to be bigger than or equal to 0. But what about the range? What can you possibly get out? Pause for a second and think, what are all the values you could get out of this function? And look at the graph for guidance. What are the y values on the graph? So the range is everything from 2 to infinity. Okay, so 2 is the absolute smallest y value we can get out, and then it just is going to keep going up. Okay. So let's look at a similar example, except we're going to do a vertical shift down. So the graph now is root x minus 2. And again, find the domain and range. So it's still basically the square root function, except we'll take a chart on the next page. Instead of adding 2 to everything, we subtract 2. Okay. So what we really have is we have the square root of x function, which we already know how to draw the graph of, and then everything goes down by 2. And we see that here. If I have my known values of root x, everything gets 2 subtracted from it. Okay, and here are the intermediate approximations of root 2 and root 3, and then minus 2. And on the graph, all that's happened is everything went down 2 units. Okay, we took the same graph of root x and moved it down 2 units. So the domain is still 0 to infinity. Okay, our function up here is root x minus 2. The only obstruction is the radical. Still just need x to be bigger than or equal to 0. And take a moment and ask, what about the range? What could I get out of this function? It's everything from minus 2 to infinity. Okay, so right here we've got that at this left point, we have this global minimum of this curve, and then there is no maximum. It is just going to keep going up and up and up. Okay, so a vertical shift, if you already know how to draw the graph of f of x, if you have the exact same function plus a number, you just take the same graph and shift it vertically up by k units. And if you know how to graph f of x and then you have f of x minus a number, you take the same graph and you shift it down by k units. This is what's called a vertical shift up or down. Okay. And again, the example we had was root x plus 2. This was up by 2 units, or root x minus 2. If you had something like this, this is totally different, okay? This is a very, very different type of transformation, but we'll see it shortly. So for example, a horizontal shift, okay? Use the known graph of absolute value, which remember looks like this, okay? To obtain the graph of the absolute value of x minus 2, find the domain and range. Okay, it's essentially the absolute value function, but it's not shifted down. A lot of students make this mistake. They see the minus 2 and they think it's a downward shift, but it's not. And what's different is that we don't have, if f of x is equal to the absolute value of x, okay, then this function here, g of x, is not f of x minus 2. That would be the absolute value of x minus 2. What g of x is f of x minus 2, aka the absolute value of, because that's what f is, the absolute value, x minus 2 is what we're plugging in. And these are totally different things. Okay? So let's look at a chart of what happens. So when x is 0, okay, oh, sorry, over here, when x is minus 2, the normal absolute value function would be 2. But our function is the absolute value of x minus 2. So this second column is values of x with specific absolute value. And then here, what we're doing is which x's, then in here, what we do is what happens, this column, what happens with g. Okay. So for example, when x goes from minus 2 to minus 1 to 0 to 1 to 2, the absolute value does this pretty predictable thing, 2, 1, 0, and then starts going back up to 1 and 2. But in order to get the same kind of behavior out of g of x, we need to do different values of x. Okay. So how do I end up with the absolute value function spitting out a 2? Okay, so to get out a 2 from the absolute value function, you need to feed in 2 or maybe minus 2. Our function is the absolute value of x minus 2. So what we need to feed in is x minus 2 needs to equal 2, or x minus 2 needs to equal minus 2. And that's exactly what these points here are. Okay, so in order to get out 2, what do we feed in? 0 or 4. Similarly, in order to get out 1, we need to feed in 1 or 3. And in order to get out 0, aka a root, then I need the absolute value of x minus 2 to be 0, and that means I need x minus 2 to be 0. In other words, I need x to equal 2 to get out a root. Okay, and I'll clear out all of this markup. Okay, so this looks like a shift to the right. Okay, in order to get the same thing that I used to get with x equals 0, because I'm subtracting 2 from all of my inputs, I now need to plug in a 2. In order to get out the same thing I used to get with a minus 1, because I'm subtracting 2 from my inputs, I now need to plug in a 1. In order to get out the same thing I used to get with a positive 2, because I'm subtracting 2 from my inputs, I now need to plug in a 4. Okay, so everything has been shifted 2 units to the right. Okay. And as I mentioned a couple slides ago, this is very much different from f of x minus 2. This is f of x minus 2. Okay. It's identical, except it's shifted 2 units to the right. What about the domain? What values of x can you plug in? Same thing. And what about the range? It's the same thing. Notice we didn't shift this graph up or down. This really is not going to affect the range. We did shift it left or right, which might affect the domain. But the domain of the absolute value function is everything, and everything shifted to the right is still everything. Okay. So how about the absolute value of x plus 2? Find the domain and range. Very similar. Okay, and we'll take a look at some values on the next slide. So now, in order to get out an absolute value of 2, instead of plugging in a 2, I need my input to be 2. So to get out 2, I need the absolute value of x plus 2 to equal 2. I need x plus 2 to equal 2, or maybe x plus 2 to equal minus 2. In other words, I need x to equal 0 or 4, minus 4, sorry. And that's what these things here are. Okay. Instead of getting out a 2 when I plug in a 2, or a minus 2, that's what would have happened with my original absolute value function. Now it's all been moved to the left by 2 units. Okay, and what about domain and range? So if I take the original black graph over here and I move it to the left 2 units, what values can I plug in and what values do I get out? Take a moment, try to answer that question. Okay, so the domain and range are identical. Okay, the original domain of absolute value was everything, and if I take everything and slide it to the left by 2 units, I still have all real numbers. And the original range was everything from 0 to infinity, including 0, and I didn't move the graph up or down, so that did not change. Okay, so if you know how to graph f of x, and you're looking at f of x minus h, this shifts to the right h units. Okay, a lot of people get this backwards. They see that minus h and they think to the left because negative numbers are drawn to the left, but it works kind of backwards when you're doing these shifts. Because remember, we're asking, what do I need to plug in? Whoops, go back. What do I need to plug in to get something out? Okay, so what do I need to plug in if I know how to graph f of 0? Then what do I plug in? If I let x equal h, I will get f of h minus h, or f of 0. In other words, I needed to plug in a positive number to counteract this negative one. Okay, that's why we shift to the right when you have a minus here. And similarly, when you have an f of x plus h, in order to counteract that plus h to get back to the graph you already know, you would have to plug in a negative number. So when you have f of x plus h, it's shifted horizontally to the left. Okay, so let's combine vertical and horizontal shifts. Graph the function x minus 3 squared plus 2, and then find the domain and range. So first ask, what is a function this is similar to that I already know how to graph? And then ask, what horizontal and vertical shifts have been done to it? And then try to answer the domain and range question, and then we'll breeze through the answers. So pause here, try to finish it up. All right, so hopefully you tried to do this. So we're going to graph it in a couple of steps. The function this is most similar to is x squared, because that's the fundamental thing that's happening to the variable here is it's being squared. Okay. And here's the graph of x squared. It was back in our library of functions in a previous section. So the x minus 3 there tells me shift it 3 units to the right. So I take the graph that I had, okay, which was like this, and I shift it 3 units to the right. But then, if I already know how to graph this, then I have the plus 2. So we had this graph right here, and I shift it up by 2. So we had 2 different steps, okay? So first we went to the right by 3 units, then we went up by 2 units. The domain is still all real numbers. There's no division here to worry about. There's no radicals. And with the range, okay, the original parabola x squared can start at a height of 0 and do anything larger than that. And we moved it to the right, which doesn't change the range, but then we moved it up by 2 units. And so our range is this right here. So we'll end this video here. The next video will deal with vertical stretches and compressions. But I will see you in a moment.